Hi all. Today we will be taking a look at the solid principles. Solid principles is a set of design principles which help the developers in developing code which is more maintainable and also helps in creating code which is less dependent on other components so that in case a component is modified, the impact of the change will be restricted to that particular component alone. Solid principle can be implemented in any programming language which makes use of the object-oriented programming concepts. So here in this scenario, I am making use of Typescript, which supports OOPS concepts. So let's take a look at the first principle, that is the single responsibility. So here in our application, we have a bank account class, which basically implements a iBank account interface. So it consists of three methods, that is the deposit, withdraw, and calculate interest. If you take a look closely at this class, you will note that the deposit and withdraw are basically commonly used properties of a bank account, but the calculate interest method does not quite fit with the functionality of a bank account. So you can say that this bank account class has multiple responsibilities, that is handling the transaction as well as calculating the interest. So ideally we should be restricting the bank account class to have a single responsibility, that is handling the transactions. So we can move this calculate interest logic, that is here you can see that actual logic to calculate the interest is embedded within our bank account. So this should be the responsibility of a separate class. So what we can do is that we can create a separate class and move this responsibility to that particular class. So for handling the interest calculation logic, I have created a separate class called interest calculator and moved that functionality to within that particular class. So now we can consume this interest calculator as a dependency in our bank account class. So here I am creating a property called interest calculator, which is of type interest calculator, and I can import that particular class. So this interest calculator we will be able to make use within our calculate interest method. So here we can return this dot interest calculator dot calculate interest method, and here we can pass the rate and the amount. And here temporarily I am creating an instance of the interest calculator class. So this way what happens is that we have moved the logic to calculate the interest to within this interest calculator, and in case in the future the logic changes to calculate the interest, that will affect only the interest calculator class and it will not make any modification within our bank account class. So this is how single responsibility can be achieved. Now let's take a look at the second principle, that is the open close principle. So open close principle basically means that when you design a class, it should be ideally closed for modification but open for extension. Let's see this principle in action with an example. So here the bank account class which I have created is basically used for handling the savings bank account. So suppose I need to handle the fixed deposit account. So one way in which you can code is that here we can create a type for our account, and based on the type, so here the interest rate might vary. So for the fixed deposit the interest rate might be more, and also here while withdrawing we might need to check whether there is any penalty in case of a fixed deposit. So one way is that we can add a type and we can put if condition here and check whether if it is of type deposit, then we can perform some logic, and similarly we can add if condition here as well. But the problem with this approach is that in case any logic changes for the deposit or the savings, this class will be handling that, and our single responsibility principle will be violated. So what you should be doing is, we should not be modifying the original class, that is the savings bank account, but you should be creating a separate class called deposit account, which will extend our bank account. So you can see that this deposit account basically overrides the withdraw method, that is the place where we need to add a check for the fine, and also here we are overriding the calculate interest, where we will be passing a different interest rate so that we can calculate the interest. So this way we will be isolating the logic for the deposit account to a separate class. So this way the deposit account will be handling the logic for the fixed deposit account, and the bank account class will be handling the logic for the savings bank account. So this is the open close principle. Now let's explore the third principle, that is Liskov substitution. So it basically means that an object of a superclass can be substituted by an object of the subclass, and it should be working fine. So in our scenario, the bank account, which is the savings bank account class, that is the superclass, and we are extending that superclass and creating a subclass called deposit account. So in our example, what we are going to do is that here I have created an Angular 13 application, and inside the app component, what I am doing is I have created an app constant where I have created two types of accounts, that is the savings and deposit. And based on this bank account types, what I have done is I have created a map in which, based on savings type, we have a savings bank account instance, and deposit, we have a deposit account. So now in the HTML, what I am doing is I am looping through the bank types, and I am displaying a button which will show the bank type. So here you can see the savings and deposit, two buttons are available, and when I click on that, it will call the get interest method and pass the bank type. So here from the entity map constant, that is this constant, using this particular bank type, I am getting the corresponding instance. So here you can see that here the type I have given as bank account. So even though the second account type is deposit account, even that is compatible with the bank account, which is the superclass. So this is the Liskov substitution principle. So what happens is that I will be able to call the method, like I want to call the calculate interest method, which exists in both the superclass, that is the bank account, as well as the subclass, which is the deposit account. But the implementation logic will be different, but the interface is same. So when I click on that particular button, the corresponding calculate interest will be called, and we will be logging our interest in the console. So first I am going to click the savings account. So here you can see that a particular amount is logged, but when I click on the deposit account, you can see that a different interest rate is displayed, which is based on the particular class implementation. But both of the functionalities work interchangeably. So this is the concept of Liskov substitution. The fourth solid principle is the interface segregation. Let's see this example. So here we have a third type of account called checking account, which is going to implement the iBank account. So since this iBank account interface consists of these three methods, when we implement this particular interface, we need to create an implementation for these three methods. But actually this checking account does not have any functionality related to the calculate interest. But even then we are forced to actually implement this method. So here you can see that I am just showing an error like the method is actually not needed. So the principle of interface segregation says that the client, that's actually the class which implements this particular interface, should not be forced to implement a method which is not actually needed by that. So what the interface segregation principle tells us is that we should be breaking down our interfaces to smaller components such that the different clients will be able to implement only the required methods. So in our case, what we can do is we can create a separate interface here called interest calculator, and here we can move that particular method that is related to the calculate interest. So here I have created a new interface called interest calculator, and I have moved the method related to calculate interest into that, and I can remove the calculate interest from the iBank account. So now what happens is that the checking account need not implement that particular method which it does not need. But in the bank account, if we want to implement that, we can implement both the interfaces. Since we can implement multiple interfaces, it is not at all an issue. So the bank account as well as the deposit account which inherits from the bank account, they will have the calculate interest logic, but the checking account which does not need that can use the iBank account interface for implementing the methods related to transactions alone. So this is the principle of interface segregation. Now let's take a look at the final principle, that is the dependency inversion. So here in our bank account, you can see that actually the interest calculator object or the class which we are using is tightly coupled with our bank account class, since we are creating an instance of this interest calculator within our bank account class itself. So the problem with this is that in case we need to replace this interest calculator with maybe a compound interest, this is basically implementing the simple interest. So suppose I have another class called compound interest calculator and I need to make use of this within the bank account. I have to go here and modify the bank account class itself. So in order to prevent that, we follow the pattern called dependency inversion. So if you are familiar with Angular, you will be familiar with the dependency injection, which follows this particular pattern. So here, using the constructor, we can accept this particular object as a parameter. So here I am adding a parameter called interest calculator, which is of type. I can give the interface. So I am giving interest calculator. So any class which implements this interface, I will be able to inject to this particular class. And here I am assigning it to the interest calculator. So now I need not create the instance here. And the interest calculator, whichever I need to use in this class, I can accept it through the constructor. So the change that we need to make is within our app constant. Here we can pass whichever instance or whichever calculator we need to use. So here, in case I want to use the interest calculator object, I can create a new one. And in case I want to make use of the compound calculator, within the deposit account, I can pass that instance. So in this way, the interest calculator logic or the class is loosely bound with the bank account. So this is the way in which we can implement the dependency inversion principle. Hope you are able to get a clear understanding about the different design principles involved within the solid principle. See you soon. Thank you.